So in this section, we're going to go through the divergence theorem. So kind of like we have Green's theorem as another way to evaluate line integrals, the divergence theorem is going to be another way that we can evaluate surface integrals. And so we know there's going to be some connection between the surface integral and something else. So what I'm going to do is I'm going to start with that divergence theorem, and then I'll give you kind of the physical explanation of what it means. And then we'll do some examples going through the divergence theorem, but also showing you kind of the benefit to doing this. So we'll do some where we don't evaluate or reevaluate a surface integral not using the divergence theorem, and then seeing what it looks like when we use the divergence theorem. So what this states is we're going to let E be a simple solid region in R3. And we're going to let S be the boundary of this region E. With outward orientation. So remember how Green's theorem, it had to be counterclockwise orientation. Here, again, you have two orientations. You have out and you have in. So if it's inward orientation, you would just negate the whole thing. If we have some vector field F, which is given by the functions P, Q, and R, where these have continuous partial derivatives. Specifically on an open region containing E. So essentially, all of these partial derivatives will be defined on that surface itself. Okay. Then what we can do is if we want to evaluate the surface integral of E, that surface S, then if we want to evaluate the surface integral over the surface of the region E of this vector field dot those normal vectors. What we can do instead is we can turn this into a triple integral where those bounds are determined by that solid E. And what we're going to have on the inside, it's kind of like we had the qx minus py. It's very similar. It's going to deal with the partial derivatives of that vector field. But the way it's going to do that is by looking at the divergence of this vector field. So remember, the gradient dot the vector field is just the divergence. So we can turn this double integral into a triple integral, and then we'll have some function on the inside, and those bounds will be determined by E. Okay? So essentially, the easiest way to kind of explain this is, again, to think about the physical meaning of the surface integral. It's telling you if F is a vector field describing the fluid flow, then the surface integral is calculating how much fluid is moving across that unit, that surface per unit time. So instead, we can relate that to the tendency of the fluid to diverge within the solid itself. Okay, so that's how we're able to get this connection between the two. You can look up other things that go into more detail about it, but that's the simplest to give the explanation. Because again, otherwise, it would take way too long to actually prove. So what I want to do is I want to go through an example of this, and we're going to work with a sphere, because we know spheres have really nice bounds. But we're going to see when it comes to actually evaluating the surface integral without the divergence theorem, it's going to take quite a bit of time, and it's not a pretty integral. Okay. So the example we're going to start with is we're going to let F be the vector field given by X, Y, Z. And we're going to let E be the solid enclosed by the sphere which is x squared plus y squared plus z squared equals 1. So the sphere of radius 1. Specifically with outward orientation. Okay. What we're going to do is we're going to find the surface integral. The surface is going to be the outer edge of the sphere over this vector field. Okay. So I'm going to start by drawing this surface itself. So we've got our sphere. You can draw in the negative axes as well because we've got the whole sphere and not one piece of it. And we'll go ahead and we'll turn these into dotted lines. Okay. So our sphere, we've got the top half of it. We've got the bottom half. And then we've got what's going on in the XY plane too, to just give it that dimension. Okay. When I go to actually calculate the surface integral in 2 dimensions, I'm going to go ahead and I'm going to need this surface here, or this region in the XY plane, because that's going to determine our bounds. And that would just be a circle of radius 1 when you look at that trace. So when you set z equal to 0, you get x squared plus y squared equals 1. So this is going to help us when it comes time to evaluate the surface integral. So I'm going to call this region R. Now what happens is, if I want to parametrize the sphere, you can use spherical coordinates, but it is going to be a little bit difficult to actually go through the integral that way. So instead, I'm going to show you how to do this with rectangular coordinates, and then we'll go ahead and we'll switch to polar when it comes time to actually evaluate the integral. So the problem also is, because this has an orientation to it, it depends on whether you're on the top of the sphere or the bottom of the sphere, the way those vectors point out. So outward orientation means it's basically like you've got spikes sticking off of a ball. So on the top half of the sphere, you have one normal vector, which points upward. And then on the bottom half of the sphere, you have a different normal vector that points in a different direction. This one is downward. So really, I need to define this using 2 surfaces. I've got S1 and S2 to indicate those separation between those normal vectors. Okay. So we're going to evaluate this surface integral first without using the divergence theorem. So if we want to evaluate this integral I, which is a double integral over S of f dot n ds, instead I'm going to split it up so I can match the orientation of the normal vector to the top and bottom half separately. So this gives me f dot n1, and then we'd have to add the bottom half of the sphere, which has a different normal vector. Okay. So at this stage, you can use spherical coordinates to do the top half of the sphere and bottom half of the sphere. The restrictions just on your phi value will be different. But instead, I'll show you how to go about this using rectangular. So we're going to look at the parameterization of S1, which is the top half of the sphere. Okay. So if I want to guarantee that, again, you can solve for z here. On the top half of the sphere, it would be the positive square root of 1 minus x squared minus y squared. The bottom half of the sphere is the negative square root of 1 minus x squared minus y squared. So when you find the vector function to parameterize this, you can use u and v, you can use x and y. Really doesn't make a difference here. So I'll go ahead, because of the way we're doing this, we'll just leave it in terms of x and y. The x and y can be whatever they want, but then the z coordinate for the top half of the sphere is the square root of 1 minus x squared minus y squared. Then considering the region that x and y go in between, it's exactly this circle of radius 1. So we'll just draw that down here, but it's the same picture I have up above. They vary in this region in the xy plane. Oh, that's new. Okay, let's make this a circle actually. There we go. So this will help us to be able to set up those bounds for that double integral. And since it's circular, probably going to be good to go to polar for this. And again, you can parameterize this a different way if you want, but me knowing how this ends up working, it's going to be easiest to use this. So you can also use the spherical coordinates, but that's going to be a trig integral that you'd have to go through, and I want to possibly avoid that. So we're going to stick to this one with polar instead. So what I need to do now is I need to figure out what goes inside here. So remember, I'm going to need the partial derivatives of each of these, and then I need to find the cross product. And I want to make sure that that cross product has consistent orientation with this upward, because it's the top half of the sphere, and that's the outward orientation. So I need to find both of my partial derivatives here. So I'm going to trust you can do this. If you find the partial with respect to x, it's 1, 0. And then this would be a chain rule. You'd have that to the 1/2 power, bring the 1/2 down out front. Then it would become the negative 1/2 power, and then you'd get a 2x attached to this. So ultimately, this will simplify to negative x over the square root of 1 minus x squared minus y squared. And then likewise, you have a pretty analogous one for the partial with respect to y. It's just 0, 1, and then negative y over the square root of 1 minus x squared minus y squared. Okay. Then I need to take the cross product of these, and I want to make sure it matches that orientation. So I'm going to start by finding this cross product. If it doesn't match, remember, just negate everything. And again, for time's sake, I think you've done enough cross products at this point. I'll tell you this ends up being x over the square root of 1 minus x squared minus y squared. Then it's y over the square root of 1 minus x squared minus y squared. And then the z component is 1. And again, this parameterization is for the top half of the sphere. So I need to make sure this normal vector, which is rx cross ry, has outward orientation. And so on that top half, it should be positive in the z component. And this does match that. So I found the right normal vector. So this is consistent with outward orientation on the top half of the sphere. So that's what we called S1. Okay. Now what I need to do before I can take this dot product, so we're in this integral, is I've got to see what is the vector field on this particular surface. So I'm going to take f and evaluate it at this vector function. Okay. And so in this case, our vector field, just to refresh off to the side, is x, y, z. So here the x and y stay exactly the same, and my parameterization for z in that z component is the square root of 1 minus x squared minus y squared. Okay. So to go through this first surface integral, I'm going to call it I1. It's the double integral over the surface S1 of f dot product with this normal vector. So in this case, it is a double integral over the region R, which is in the xy plane, of this vector. Dot product with this normal vector, which is Rx cross Ry. So dot product with x over square root of 1 minus x squared minus y squared, y over the square root of 1 minus x squared minus y squared, and then 1. And then we're going to integrate this with respect to x and y. Okay. So I've got to go through this dot product. We'll worry about setting up the bounds afterwards, but just matching those like pieces, we get x times this first component. So that leads us to x squared over the square root of 1 minus x squared minus y squared. Okay. Then our second component is y times y over the square root. So that just leaves us with y squared over exactly the same thing. And then adding the last piece, we get this square root times 1. So it just becomes that square root. And then this whole thing I'm going to integrate with respect to x and y. Okay. So I'm hoping that this is going to simplify. If you notice, the first two have the same denominator. So to be able to add all of these together, I need this with the same denominator. So really all I'm going to do is I'm going to multiply the bottom by the square root of 1 minus x squared minus y squared. But then really you would do the same thing in the top to make that common denominator, which is nice because it'll end up canceling that square root. So this is a double integral over the region R. Now every single piece is going to have the square root of 1 minus x squared minus y squared in the bottom. I don't actually need parentheses at that point anymore because it's a single fraction. And then we get the first fraction plus the second fraction, and then when you square that last piece, it becomes 1 minus x squared minus y squared. So thankfully some nice stuff happens. The x squared and y squared disappear, and this becomes the double integral over the region R of 1 over this. And then we're going to integrate with respect to x and y. Now at this point, you definitely could set this up using x and y bounds, but integrating that inside is not pretty. So this is where this region of integration comes into play. So because it is a circular region, it's going to make a lot more sense to integrate this with polar coordinates. So the inside will become 1 over the square root of 1 minus r squared. The dA becomes r dr d theta. And then since this is a circle of radius 1, this is going to have r bounds from 0 to 1, and it's the whole circle, so the theta bounds are 0 to 2 pi. Okay? And then this is separable, so you have the integral from 0 to 2 pi of just theta. And then thankfully, this r integral we can just make a u sub for. So you get 1 over the square root of 1 minus r squared times r dr. So if we let u equal the thing inside the radical du is going to be negative 2r dr. I don't have that negative 2, so not a problem. Negative a half du is r dr. Then I'm also going to go ahead and change those limits. So if r is equal to 0, my u is 1 minus 0. When r is 1, u is 1 minus 1. So the bound goes to 0. This first integral we've done countless times. It's just going to be 2 pi. Then we can go ahead and evaluate this. So we get negative a half. My lower bound changed to 1. My upper bound changed to 0. And it gives me 1 over the square root of u du. Okay. And then you can go ahead and get rid of that minus sign. We'll just switch the bounds. And then also the 2 and the 1/2 cancel. So that minus sign gets sucked into the bounds to switch it to be from 0 to 1. And then we integrate u to the negative a half du. So thankfully this is nice. That becomes u to the positive 1/2 divided by a half becomes 2. Evaluated from 0 to 1. This surface integral ends up equaling 2 pi. Okay? So we did the first half of this problem. We've gone ahead and we figured out that the top surface integral is going to equal 2 pi. Now I need to do the same thing, but I have to go through this with a different parameterization for the bottom half of the sphere. So that leads us into the parameterization of S2. Which is the bottom half of the sphere. You're really going to use exactly the same thing. The only difference is that the z component is going to be negative to be the bottom half of the sphere. So I do want to go ahead and I just want to bring all of these pictures down just so we have it. Just to save us a little bit of time from copying it, we can at least shrink them a little bit. So if I want to go through this parameterization, again, I'm going to use the same kind of vector function. We can use x and y. As you can see, it turned out really nicely for this last problem instead of using trig functions. In this case, our x and y are exactly what we want, and the z component is the negative square root. We then also need to find those partial derivatives, and then we need to find the cross product. So if you take the partial with respect to x, it will give you 1, 0. And then the only difference is here when you have that minus sign that pops out from the bottom, it'll cancel. So this will be x over the square root of 1 minus x squared minus y squared. And then likewise, the partial with respect to y is 0, 1, y over the square root of 1 minus x squared minus y squared. Now I need to find that normal vector, and it needs to match the outward orientation. So on the bottom half of the sphere, for outward orientation, my z component should be negative because they have to point downwards. So if you go through and you find this cross product, it's going to end up being negative x over the square root of 1 minus x squared minus y squared. Negative y over the square root of 1 minus x squared minus y squared. And then you'll get a 1 in this component. Okay. So this is a problem. This cross product is not consistent with outward orientation. On the bottom half of the sphere. But that's okay. We don't need to do any extra work. all it means is we would find the other cross product, but all that does is negate each component. So now this becomes positive x, positive y, and then negative 1. So now it matches the downward orientation. So this is consistent now. Okay. So we're doing good. So what ends up happening is when I go to actually evaluate the surface integral, which is a double integral over this region R of f dot this normal vector instead, what you end up with is a double integral over the region R. F is xyz, so this is x, y, and then the z component is the negative square root from right back up here. And then we're going to dot product this with x over the square root of 1 minus x squared minus y squared, y over the square root of 1 minus x squared minus y squared, and then negative 1. Okay. So realistically, it looks almost identical as the last one. The only difference is these are both negative, but that will make it positive, and really this ends up being exactly the same integral, because the inside becomes x squared over the square root of 1 minus x squared minus y squared plus y squared over the same thing. And then the last becomes positive square root of 1 minus x squared minus y squared. So you would simplify this in exactly the same way. You'd still use polar coordinates to evaluate this. This is exactly the same as I1. So I do not need to do any work. I know this is equal to 2 pi. Okay. So what that means is that this entire surface integral is equal to the sum of both of these, which gives us 2 pi plus 2 pi for a grand total of 4 pi. All right. So you can see a lot of work because of the two different surfaces that are in here. Even though it ended up being the same integral, it doesn't always play out that way. What we're going to do now is the same thing, but using the divergence theorem. Okay. So our vector field F is again x, y, z. Our solid E is the sphere of radius 1. Okay. So when I go to evaluate this surface integral, instead I'm going to integrate over E with the divergence of the vector field, and then integrated with respect to x, y, and z. So you can directly find the divergence in here because it's not too bad of a vector field. You could also do it beforehand off to the side. I'll show you in here. Remember, the divergence is you take that vector of all the del operators, that should be a y, and that should be a z. I keep wanting to write x every single time. And then we dot product this with x, y, z. So this gives us triple integral over e of the partial with respect to x of x, the partial with respect to y of y, and the partial with respect to z of z. And thankfully, these partial derivatives are just equal to 1. So this ends up being a triple integral over e of 3. Well, if you pop that 3 out, what you're left with is the triple integral over e with 1 on the inside. And so remember, if you have a 1 inside of a triple integral, all that means is find the volume of E. And it's a sphere, so we have formulas for that. The volume of a sphere is 4/3 pi times the radius cubed. The 3 and 3 cancel, and this leads you to 4 pi. The exact same answer, but without as much calculations needed. So this theorem is awesome because a lot of times it does end up resulting in a much simpler integral with less calculations that we have to do. So we're going to try just 2 more examples of this. For these next ones, I'm not going to go through the standard surface integral. Instead, we'll just jump into how do we use the divergence theorem. And this next one, you'll also see the beauty of why this divergence theorem is nice. So it's going to have pretty similar directions for all of these. You're going to be given the vector field. You're going to be given the solid. You want to find the surface integral over that. So I'll write out the full directions for this one. Let f be the vector field 3y minus 4x, 3z minus 3y, and y minus 5x. And we're going to let E be the solid cube given by the following. It's all the x, y, and z triples such that x is trapped between -1 and +1. Same with y, and same with z. We're going to go ahead and we're going to use the divergence theorem to find the double integral over the surface of f dot n, where S is the surface that encloses E with outward orientation. So just to draw you a picture of this solid, put in all of those negative components, and then go ahead and make these dotted. So our x is trapped between -1 and +1, which say is right here. Same thing with y, and then same thing with z. So it is the cube that is going through all of these. So the side lengths of these cubes would both be 2. Because you have 1 to -1 on both of them. And then it goes backwards the same distance. And then you could go sketch in the other components if you want to, but we don't need to go through it. But all of these side lengths are all going to be 2. Okay. So this side length 2, this side length 2, and this side length 2. So this is E. So if I didn't want to use the divergence theorem and I wanted to find the surface integral, you'd have 6 different surface integrals that you'd have to evaluate, because on each one of these you have a different parametrization and you have a different normal vector that's pointing outward. And then here in the front it would be pointing out like this. So if we didn't use the divergence theorem, we would have 6 surface integrals. To evaluate. But instead, I can just do a single surface, okay, or a single integral, triple integral. So the first thing I'm going to do is figure out what goes on the inside of my triple integral. So I want to find the divergence of this vector field. So again, that means take my gradient vector and dot product it with f. So that's the vector of all of my partial derivatives. Dot product with 3y minus 4x, 3z minus 3y, and y minus 5x. So for some reason my minus didn't stick. So going through, this means I take the partial with respect to x of this first piece. I add the partial with respect to y of the second piece. And then the partial with respect to z of this last piece. This first partial is -4. Second partial is -3. Last partial is 0. And this is fantastic because the inside then just becomes the number 7. So my surface integral over this entire surface becomes the triple integral over this cube E. And then we put the divergence of our vector field in here. Well, that's just -7, so I can go ahead and just pop that out. And what's left then is the triple integral over E of dv. And again, when that's the 1 on the inside, that's best case scenario because then I'm just finding the volume of E. And a cube is a shape I do not need to set up a triple integral for. So it's a cube with all of my side lengths equaling 2. So this is -7 times 2 times 2 times 2. So it's really -7 times 8. This surface integral would equal -56. Wrote 8 because I said 8. Right? So again, much quicker, much simpler than setting up 6 different surface integrals with 6 different parameterizations, 6 different partial derivatives and cross products that you'd have to take, and then evaluating that vector field along all of those. A single surface integral would take long enough, but 6 would be a lot. So let's try one last example of this to see the benefit. So let's let f be the vector field to x, y, z, and s is the surface that encloses the solid bounded above by z equals 6 minus x squared minus y squared, and below by z equals 0 with outward orientation. We're going to evaluate the surface integral of f dot n ds. Okay. So again, if I want this surface integral, it's a solid enclosed by these two things, so it ends up having to be 2 different surfaces. To just give you that visual, 6 minus x squared minus y squared. If you look at those traces, you would get paraboloids or parabolas in each trace. So this forms a paraboloid. When you plug both x and y equal to 0, it would go through 6. You'd have a parabola in the yz trace. You'd have a parabola in the xz trace. And then when z equals 0, you'd have that circle. Okay. So down here, if z equals 0, you'd have 6 equals x squared plus y squared. So it is a circle of radius root 6. And it's got outward orientation, so that means those normal vectors look like this. So this is our solid E. So again, you absolutely can do two surface integrals, but this one's really nice that we could go ahead and set this up with a triple integral. So we're going to go and use the divergence theorem for that. So I also want what's going on in the xy plane because that's going to be useful for setting up those bounds. And if you look at what's going on in the xy plane, because it is a circular region, it's going to make a whole lot of sense to use cylindrical coordinates here. So we've got x squared plus y squared equals 6. So this would be root 6, negative root 6, positive root 6. Okay. So since I want to use the divergence theorem, it's going to make a whole lot of sense to go ahead and find the divergence of this vector field. And you don't need to go ahead and write out that it's the gradient dot product. You're going to go ahead and just take the partial with respect to x of the first component, which is 2x, the partial with respect to y of the second, and then the partial with respect to z of the third. And thankfully, these are all really nice. That's 2, 1, and 1. So the divergence of this vector field is 4. Okay. So if I want this surface integral, instead we turn it into a triple integral determined by E of the divergence of the vector field. So this becomes 4 on the inside, and then we'll go ahead and set up these bounds. But we're going to integrate with respect to dv. I'm going to set this up using rectangular coordinates first, just so we get some practice with that. We'll do dz, dy, dx. So our z value starts at 0 and then goes up to this function. So the bounds are 0 to 6 minus x squared minus y squared. Then looking at the xy plane to figure out what's going on, the x is the easiest because it's the constants. So that's negative root 6 to positive root 6. For the y, you would start at the bottom half of the circle and go up to the top half. So that would be negative square root of 6 minus x squared to positive square root of 6 minus x squared. So these would be those bounds on y. So this is using rectangular coordinates. But again, because it's that circular, it's going to make a lot more sense to use cylindrical. So this turns into a triple integral still, and then the dy dx turns into r dr d theta, and z just stays as is. For the bounds on r, or on z, we go ahead and look at z's component. This still goes to 0. X squared plus y squared turns into r squared. So the bounds on z are 0 to 6 minus r squared. Then my r bounds, the radius of the circle is root 6, so it goes from 0 to root 6. And then we go all the way around the circle, so we go from 0 to 2 pi. So again, much nicer integral, not as complicated bounds, not as many variables in here. Before I can start separating this thing, I need to at least go through this first integral. Antiderivative of r with respect to z is rz, evaluated from 0 to 6 minus r squared, and then we're left with dr d theta. And then realistically, you could have pulled this out. The inside's going to become separable, so you get 0 to 2 pi d theta, and then from 0 to root 6 of r times 6 minus r squared, integrated with respect to r. So the integral from 0 to 2 pi of d theta just becomes 2 pi. And then here we're integrating from 0 to root 6 of 6r minus r cubed. And this gives me 8 pi. Antiderivative of that would be r squared over 2, so we get 3r squared. And then 1/4 r to the 4th. And then I trust when you plug in 0, everything just becomes 0. When you plug in root 6 squared is 6, and then root 6 to the 4th would become 36. You can definitely go through all this. You should get this. This ends up equaling 72 pi. Okay. So this is another way, again, it's kind of analogous to Green's theorem. Green's theorem gave us a way to turn that single line integral into a double integral. Here, divergence theorem allows us to take this double integral and turn it into a surface integral instead, which can be easier to calculate. If you have multiple surfaces, you would have to parameterize.